Hi, I'm Dr. Califf, and today I'd like to talk about using data in machine learning for training, validation, and testing. Learning in general requires data, usually quite a lot of data. Now, sometimes we're lucky and what we're trying to learn is something that we can just gather the data that's already on the internet, though we should be careful about things like copyright laws, and we may not need a lot of work to use that data. Then we've got plenty. More frequently, however, we do need labels on our data. Somebody's got to actually identify what we're trying to learn about each instance of data that we have. This can mean long hours of work, often by underpaid graduate students. We've put in some time and effort and maybe money on this data. So then once we have all the data, we would often ask the question, why split it? Don't we want to just use all of this data that we've gathered at such cost and effort for the training? Let's think about that for a second. Think about what we want to learn. Imagine a math teacher gives a set of practice problems to her students. A few of them decide to just memorize the answers to the problems. Others actually try to learn how to work the problems correctly. If she gives a test that is a subset of the problems that she provided them, who's going to do better? They might all do the same, but it's quite possible that if the memorization was good, the people who did the memorizing would do better. But do we think that they're the ones who learned the material the best? What if instead she gives similar problems, but not the same exact problems? Then who does better? As we think about that, let's note that machine learning systems memorize. At least they can memorize. We don't really want to know how well the machine learning system does on the data it was trained on. What we want to know is how is it going to do when we give it new data to work with. Otherwise, we don't have a lot of point in the system. We already know the answers for all of the existing data. We want to know, as new data comes in, what are going to be the answers for that. If we just test on the training data that it's already seen, we can't tell whether it just memorized those or it will do well on new data as well. If we hold back some of our data as an unseen test set, some data that the learning model hasn't actually seen yet in developing it, then we can get a better idea of how it's going to actually do by how well it does on that test data. Note that we want that test set to be reasonably large because a larger test set is going to typically provide us with better statistics, better ways to evaluate how well we're going to do on this data that we haven't trained on. That gives us a better idea of how our model is really going to perform in the real world. Now there's training, there's testing, and then a lot of people don't know what might be meant by validation. Learning algorithms can often be tuned, and validation is sometimes called tuning. For example, neural networks have what are called hyperparameters. Some examples of this would be the size, so how many nodes do we have in the hidden layers of this network? What algorithm are we using? We have a number of different choices for that. How much are we updating weights by? What are our starting weights? There are many, dozens typically of these things that we can tune about a neural network. Getting away from neural networks, other kinds of learning also can have tuning. For example, if I'm learning a decision tree, which is a typical non-neural network kind of learning model, we have pruning that we may do. So we may not want to build the decision tree just as big as it can go because it'll have little decisions at the bottom, and so we want to do pruning. We need to be able to make decisions for these tuning, pruning, hyperparameters with data. Otherwise, we're just wild guessing. We want to be able to use data so that we can feel confident that we're making the right decisions. What do we want to validate with? Training data is not going to be very effective because it's what we're training on. Trying to tune the data with the same data that we're training with doesn't really tell us much. Test data, using the test data for both this tuning process and for actual testing, ends up being cheating, and we end up with the same kinds of issues, maybe not as badly as if we use training data for our testing, but we've tuned the model to match the test data. So the results that we're getting are not indicative of performance on totally new unseen data because we've tuned this model. Although it's been trained on other data, it's been tuned specifically toward this data. So that means we need a third set of data. This one can usually be a little smaller than the testing and training data sets, but it needs to be significant enough for us to get a good sense of how our tuning is working on new data. So, building a good learning model requires plenty of training data. How much you need depends on your problem, on the particular kind of model you're making, but you need to make sure you have enough if possible. Sufficient validation data that you haven't used for training to tune the model if your learning algorithm is tunable. Some algorithms are not, many are, and of course in the current world of neural networks being the big thing, very tunable. And finally, sufficient testing data that you haven't used for either training or validation to predict how well your model is actually going to work when it gets out into the real world. Thanks for watching. If you found this video helpful, I hope you will help others find it by liking and subscribing. And if you're new to the channel, I encourage you to check out some of my other videos.